This module is on work and work energy theory. First of all, let's introduce the definition of work done by a certain force on an object. What is work? Work is integral. It's always a definite integral from R1 to R2 F dot dr. This is dot product, which means that work is a scalar. Work is a scalar and always a definite integral. Now, we need to understand what each symbol means in this formula. Force F is force acting on the object. What is dr? Imagine that this object is moving from point x1, y1, this is x1, y1, to a point x2, let it be somewhere here, to a point x2, y2. This is described by vector r1 from the origin to the point x1, y1. And this one is described by vector r2 from the origin to point x2, y2. And this is the trajectory. This object is moving along this line from point r1 to point r2. So what is dr? dr is infinitesimal change in displacement when this object is moving along this trajectory. Infinitesimal change in the displacement. What I will do next, I will write each of these vectors, f and dr, in terms of components. We can do that. We already introduced unit vectors I and j. So here is a unit vector I, and here is a unit vector j. And any vector, as we know, could be written as, in terms of components, is as fxi plus fyj. I will do the same with vector dr, infinitesimal change in displacement. dr is dx, where dx is x component of dri, plus dyj. And now I will bring these two in my definition. Work is equal to integral. R1 is x1, y1. R2 is x2, y2. And then I have f, which is fxi plus fyj. Dot product with dr, which is dxi plus dyj, and this is equal to, let's take this dot product. But before we start doing this, let's remind ourselves, what is dot product? If I have two unit vectors, I and I, what is dot product I dot I? Remember, dot product, magnitude of the first one, 1, magnitude of the second one, again 1, times cosine of angle between them. What is cosine of angle? Angle is 0 between I and I. Cosine 0 is 1, so dot product is 1. What is I dot j? Magnitude of 1 of the first vector, which is 1, times 1 times cosine of 90 degrees, which is 0. So dot product of perpendicular vectors is 0. And we remind ourselves that every time when we are calculating dot product, when we calculate work, we are looking for parallel components of force and displacement. Now let's finish this line. Let's find this dot product. What is dot product? I dot I, it is 1. So I have integral x1, y1 to x2, y2. And I have fx dx, f sub x dx. And I dot I gives me 1. Then I take dot product. J dot j again gives me 1. So I get another part of this integral from x1, y1 to x2, y2. And here I have fy dy. And then I dot j, wait a second, I dot j and j dot I will give me 0. So we are done. We wrote the definition of work here, integral, definite integral from R1 to R2 f dot dr. I will rewrite it in terms of components of force and dr. So it will be from x1, y1 to x2, y2. And then I have projection of force in x, f sub x dx, plus fy dy. From x1 again, y1 to x2, y2. Consider this. Force does not depend on position. It is constant. For example, force of gravity. Or we are pulling something with the force that is the same as object moves. It does not depend on the coordinate. I will call it F naught, emphasizing that this is a special case when force does not depend on the position. Now let's look at our definition. And what do we have? First of all, why am I doing this? Why am I considering this case? I want us to understand how our previous knowledge that we had in high school or somewhere in the middle school, what is work? Force times distance, or there is some angle between them. How does our previous knowledge fits this new definition? So, this special case, force is constant. I use my definition, force is constant. I take it out of this integral. What will I get? I will get F naught dot integral dr. This is displacement. I will call it dr. In many books, the displacement is called d with a vector. I will call it dr for us not to mix this d, which is differential, with the displacement. So this is our new formula for work that we knew before, probably. What is this? It is magnitude of the first vector, which is F naught, magnitude of the second one, dr, times cosine of angle between them. So if this is my displacement, dr, this is force, F naught, and this is the angle theta, then F naught delta r and cosine theta. Next, I will consider even more special case. What I will do, I will move the object from x1 to x2 along the line, and the force acting on this object will be along x. This will be my F naught. So force will be, I will put this notation for that. Force will be in the same direction as the displacement delta r. And remember, force is still constant. So let's find work done by this force F naught. What will be the work? Work will be, I will look at this formula first. It is F naught times the displacement, magnitude of the force, F naught, times magnitude of the displacement, x2 minus x1, times cosine of angle between them, which is 0. Cosine 0 is 1. This is work done by this force F naught. Now let's look at our definition that always works. This is the general formula. So what is F sub x? It is F naught. F naught. What is in, and it is constant. Since it is constant, I just take it out of this integral. What is integral dx? It is x2 minus x1. It is x, and limits will give me x2 minus x1. second part of the integral, Fy. Fy is 0. The force is along x. So that part of the integral is 0. And yes, of course, we got the same answer from our general formula that always works. I want to emphasize that this work is positive. So force is in the same direction as the displacement and work is positive. Now we will consider next special case when I move the object again from x1 to x2. And the force acting on the object will be now in opposite direction to the displacement. This is the force F naught. The object moves to the right. This is the direction of this displacement, delta r. So what will be work done by this force? Work done by this force. Let's look at this formula. Magnitude of F naught. Magnitude of delta r, x2 minus x1, the displacement. And then cosine of angle. These two vectors are anti-parallel. Force is in the opposite direction. Force is in the opposite direction to the displacement. So, magnitude, cosine of angle. Angle is pi. They are anti-parallel. Cosine pi is -1. And I will write this minus here in front of this formula. So, work in this case is negative. Force and displacement are anti-parallel. Now let's look at our main definition. What is F sub x in this case? F sub x is minus F naught. Integral dx, x2 minus x1, Fy is 0. We don't have this part. And yes, we calculated work done by this force F naught that is anti-parallel to the displacement. Now, next case will be, I'm moving object again from x1 to x2. But in this case, this is x from x1 to x2. But in this case, the force acting on this object will be at some angle. Angle, this is force, and this force will be at angle theta with horizontal. And the displacement x1, x2 is along the horizontal. So now let's calculate work done by this force F naught. What is work? It is magnitude of force F naught, then magnitude of the displacement x2 minus x1, and then cosine theta. Cosine theta. This is our formula. Now, let's look at our definition and figure out how do we get the same formula from our definition. What is F sub x in this case? F sub x, I draw the line perpendicular to x. This is my F sub x. F sub x is F naught cosine theta. F naught cosine theta. This is F sub x. Times, since this is constant, what is constant? Force is constant. It is always at the same angle theta. Theta is also constant. So I take F naught cosine theta out of this integral. Integral dx is x2 minus x1. And of course, we got the same formula. However, what about the second part? Why did I skip it? I do have Fy. I do have non-zero Fy in this case. Let's look at the limits. What is the displacement in y dimension? What is y1? It's 0. It is on the surface. What is y2? It's again 0. So the limits will be from 0 to 0 in y. The displacement is 0. That's why the second part of this formula, the second integral, will be 0. As always, we are looking for parallel components of force and displacement. That was our part C. And the last case that we will consider, part D, will be when object moves, as always, from x1 to x2. But in this case, so this will be my delta r, the displacement is to the right, but the force acting on the object will be, for example, down. This will be my F naught. Now, what will be work done by F naught? Oh, look at this. Force is perpendicular to the displacement. Then dot product will be 0. Or, in this case, the projection of force on x will be 0. So the first part of this integral will be 0 because f sub x is 0. The second part of this integral will be 0 because I do have non-zero fy. However, the limits are from 0 in y to 0 in y. The object doesn't move in y direction. This is x. So y2 minus 1, y1 will be 0, and work will be 0. Force is perpendicular to the displacement. Work is 0. I hope that these specific cases help you to connect this formula for work that works only for the case of the constant force with our new definition that is always true, because we will consider the forces that are functions of x and y, forces that change when we move objects from point 1 to point 2. They will depend, these forces will depend on the trajectory, and we will have to use this definition and these integrals. The last formula that we need to write, a very important formula that we will be using in this unit, will be work energy theorem. What is work energy theorem? Imagine now that instead of calculating work done by a single specific force, you calculate work done by the net force. What is net force? It is vector sum of all forces acting on the object. Then I rewrite the definition from R1 to R2. F net or total dot dr. You can calculate net force and calculate work done by the net force. Or you can calculate work done by each forces acting on the object and then add them together. But what's important, that work done by the net force is equal to the change in the kinetic energy. mv2 squared over 2, where 2 corresponds to the final, minus mv1, where 1 corresponds to initial, v1 squared over 2. And this is the work energy theorem that we will use a lot when we solve problems in this unit.